Welcome to the wonderful world of analysis. In this video we're going to explore multiplication of power series. Now multiplication of power series, we're going to see it's a little bit more delicate than things like addition and subtraction. Addition and subtraction of power series, you can just pair up like terms. It's pretty simple, pretty straightforward. But when we're multiplying, we're going to have a large number of cross terms. To build some intuition for what we're going to do, we're going to look at the partial sums. Now the partial sums are of course polynomials. So we're going to start by looking at multiplication of polynomials. And of course the idea is for multiplication of polynomials, what makes this interesting is we have cross terms. So we have lots of terms that can interact with each other, like this a0 can interact with every term in the second polynomial. So what we're going to do is we've left this fairly vague. I haven't told you what n is, I haven't told you what m is. I'm not going to actually multiply the whole thing out. That would take a long time, depending on what m and n are, potentially hours and hours and hours. So instead what we're going to do is we're going to look for patterns and we're going to take advantage of those patterns. Right? That's what mathematics is. We're trying to take advantage of patterns. So what we're going to do is we're going to find the coefficient, let's say on x to the k. Let's try and figure out what would do that. Well, to do that, we know if I take a 1, I need to multiply that by an x to the k from over here to get an x to the k. So let's see, we'd get things like an a0 times x to the 0. That's 1 is x to the 0. That would get multiplied by b sub k times x to the k. Okay, so if I go to the next term, I have a1 times x. Try and figure out what term over here I'd need to multiply. Well, I'd need b sub k minus 1 times x to the k minus 1. And let's see, what's important here? On this first term, if I look at the powers, I have x to the 0 times x to the k. That adds up to k. X to the 1 times x to the k minus 1. That adds up to k. Next term, if I have x squared, I need to multiply that by x to the k minus 2. Of course, and this can keep going on for quite some time. And not all of these necessarily make sense. If I pick k to be 0, right, I only get this first term. Right? But all the terms that come in here, there is a pattern to them. The powers of x add up to k, and in fact the coefficients, the little indices here, add up to k as well. So if we put this all together, we get x to the k times, we'll have a0 times b sub k, plus a1 times b sub k minus 1, plus dot dot dot, all the way up to a sub k times b sub 0. So there is a definite pattern, there's some structure to how these things are put together. Now the idea is, this is what we're doing for polynomials, that is the partial sums. Everything with infinite series is run through partial sums. This is exactly how multiplication of power series works. We're going to define the multiplication of two power series as follows. So I have one power series with a sub n's, another power series with b sub n's. It's going to give me a third power series, sum n equals 0 to infinity, c sub n times x to the n, where the coefficients c sub n are defined by this finite sum k equals 0 to n, a sub k times b sub n minus k. Okay? This is what we're going to call the product. Now this, of course, you notice the pattern stays the same. We're going to add up these coefficients. The indices have to add up to n. A sub k times b sub n minus k, add those together, we get k. Now such tools here, these are terribly, terribly useful, terribly important in fields such as complex analysis, and complex analysis has applications in PDEs and calculating real valued integrals, all sorts of places. So we want to figure out what's going on here. So let's figure out what happens with convergence. So one theorem that's terribly nice is if I have an absolutely convergent series, some a sub n absolutely converges, then of course it converges. So some a sub n, let's call that a, and we're going to have a different series, we'll call that some b sub n, let's call that b. Okay, then the product series, the series of the product, is equal to a times b. Okay, so before we get too carried away, it's important to notice this assumption is very, very important. This fact that the series is absolutely convergent. It converges absolutely. That is critical to the proof. And in fact, without it, the statement itself can be false. So let's prove this. And of course, anything we're going to prove with infinite series, we're going to look at partial sums. So we're going to define the partial sums of the three series in question. Capital A sub n is going to be the partial sums for the first series, capital B sub n, partial sums for the second series, and capital C sub n, that's what we're really interested in. This is the partial sums for the product series. So let's look at C sub n. C sub n, if we start, should actually start with C0 plus C1 plus C2 dot 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 up to Cn. Okay. What we need to do is we need to figure out how can we show this tends as n goes to infinity to a times b. Now, as it's written right now, it's not very helpful. We need to really take advantage of the structure that we've got here. So let's write out what these actually are. C0, those are the things where the indices add up to 0, so a0 times b0. Then we're going to have C1, okay, so that's A0, B1 plus A1 times B0. And we're just going to keep adding these up here. This last term, these are all in C sub n. Okay, so now what can we do with this? Right now, this is not all that much more useful. What we need to do is we need to start collecting things. So I notice there's an A0 in this term, an A0 in that term, there's an A0 in the next term, there's an A0 in every term. So if I collect all the things with A0, I'll have A0 times B0. Let's A0 times B1, dot, 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 everything's got an A0. If I go to the next term, A1, well, A1 is in almost every term, just not the first one. So A1, we're going to get a lot of B's multiplying A1 as well, and I can keep doing this. After that, I'll have an A2 in this next term. Everything else will be taken care of. I can put these all together. So really what we're doing here is we have A0 times all of the sum of the b's. So that's our capital B sub n, a partial series. A1 is going to be a partial series. It doesn't go quite as far. It's going to stop at B sub n minus 1, and we can continue this product. So now we have a different way of writing this. Sum k equals 0 to n, a sub k times capital B sub n minus k. Okay, so we're a little bit closer. We still should play around a little bit with this, okay? Because capital B sub n, that's something we know about. We can work with that. We're going to try and write everything in terms of that. So the first term, A0 times B sub n, that's perfect. We'll have A1 times B sub n. Well, it's not quite, it's B sub n minus 1, so that's just one term away. So we'll do B sub n minus little b sub n. Okay, and similarly, we go to the next term. It has two terms we need to take off, B sub n and little b sub n minus 1, and we can keep going with that. And we're in a pretty good place here. So now let's define beta sub n. Beta sub n is really going to be the difference between our partial sums of b and its limit. Okay, it's sort of an error term here. Then we can rewrite our partial sum c sub n as, well, we'll have a0 times, just doing a little rearrangement, add b over here. Little b sub n is beta n plus b. And then a sub 1 is going to be b plus beta sub n minus 1, dot, 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 up to a sub n times b times beta sub 0. So we're in a pretty good place here. Let's see what we've got. We've got a lot of things with b, and that's good. We want b, so we have a0 has a b, and a1 has a b, and a2 has a b, a3 all the way up to a sub n. Okay, and then what we're going to have is we're going to have a lot of, let's just call them for a minute, other stuff. Okay, so this is looking pretty good. We've got capital B times a partial sum, capital A sub n, plus this other term. So this other term, well, let's see, if we put this all together, really we could rewrite this as a sum k equals 0 to n. Let's see, we'll have a sub k times, well, let's see, a0 is times beta sub n, a1 is times beta sub n minus 1. It's going to be beta sub n minus k. Okay, so what we have right now is we have a piece. This, I think, is pretty clear that this is going to converge to b times a. This is what we want. Right, because this is the sequence of partial sums for a, we multiply it by some number b, that's going to converge to exactly what we want. So what we want to do is we want this to go away. We'd really like to be able to show that this goes to 0. Okay, if we can do that, we're in good shape. So in fact, that's exactly what we need to do. We can show that this limit as n goes to infinity, the partial sum c sub n converges to c equals a times b. That's important, that's what we're trying to do, if we can show that this other part goes to 0. Now to do this, we do need a little bit more machinery here. We're going to define the number alpha to be the sum n equals 0 to infinity of the absolute values of a sub n. Okay, this is why we need the series to be absolutely convergent. We need this number to make sense, and without losing too much, we can assume this is a positive number. Okay, because if it's not a positive number, if alpha is equal to 0, then every a sub n is equal to 0. That series is equal to 0. 0 times anything is 0. This is a pretty trivial theorem. Okay, so this we can assume without losing anything is a positive number. And then, since our series of b sub n's is convergent, Given any epsilon greater than 0, we're going to take arbitrary number epsilon greater than 0. By definition of convergent, there exists a natural number n sub 1 so that b sub n minus b gets small. That's exactly the size of our error. This is beta sub n in absolute value. We can make this small. We're going to choose it to be smaller than epsilon over 2 alpha for all n greater than or equal to capital N sub 1. Okay? This value, it's not just picked out of the blue. This is something that's going to make our proof get to a really nice, pretty ending in just a few minutes. So this is not the first draft. This is why we chose epsilon over 2 alpha. Now similarly, I'm going to let gamma be the supremum over n, the absolute value of beta sub n's. Now again, this is going to be a positive number. Okay? It's positive, otherwise our series B is really, really boring. It's exactly the 0 series. Okay? And if it's exactly the 0 series, there's nothing to this proof. So we're going to assume that this is positive. We don't lose anything by that. We only have to throw away one very uninteresting case. And we can also be guaranteed that this is a finite number, since our series beta sub n, it came from a convergent series. This is going to 0. So it is definitely a finite number. Okay, so now let's see what we can do with this. Okay, once we have these, we're in a pretty good place. And now we can use one more fact. Since our series a sub n converges, right, it's absolutely convergent, so it's conversion. Its sequence of partial sums forms a Cauchy sequence. We've proven that. So there exists a natural number n2 such that absolute value of a sub n minus a sub m is going to be as small as we like. In this case, we're going to choose as small as we like to be epsilon over 2 gamma for all n greater than or equal to capital N2. Okay, now we can get about proving that funny term actually goes to 0. And of course, we're going to prove it goes to 0 by showing it's less than this arbitrary value of epsilon. Okay, so let's take little n greater than or equal to 2 capital N, which we'll take to be capital N is going to be the max. So this is capital N is the max of n1 and n2. So now let's look at this term we have. It was the sum k equals 0 to n. We have a sub k times beta sub n minus k. Okay, so now what I'm going to do is I'm actually going to break this up into 2 pieces. I'll use the triangle inequality. I'm just going to take the first few terms here. I'll have a0 times beta sub n plus a1 times beta sub n minus 1, and I'll keep going. I'll pick off about the first capital N terms. Okay, so I'll get down to, let's see, I'll have a sub little n minus capital N minus 1 times beta sub capital N plus 1. Okay, and then I'm going to add to it the remaining terms. So the triangle inequality is because I broke this up. I'll have beta sub n times, well, let's see, a sub capital, no, excuse me, a sub little n minus capital sub n, dot, 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 all the way down to, at the end, we'll have beta sub 0 times a sub n. Okay, so what we want to do is we want to show this is small. So let's look at these first terms here. All right, here I've got beta sub capital N plus 1. The next one will be beta sub capital N plus 2, and so on. All these indices on beta are greater than n. And that's great because I know beta sub n is smaller than epsilon over 2 alpha as long as I let n get large enough. And since n, little n, is greater than the maximum of n1 and n2, it's certainly bigger than n1. Okay, so all these things I can break out. This is going to be smaller than this first term. I'll have epsilon over 2 alpha. And then let's think about what's left. Everything in here, I'll have a0 plus a1 plus dot, 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 up to a sub n minus capital N minus 1. Okay, so that's not too bad. I've certainly got the epsilon in here that I'd like. And then the second term, well, let's see, I could make this bigger by just pulling out the absolute largest value of beta sub n. Okay, because all these have some beta times them. And then I'm going to have, well, let's see, I'll have a sub n minus n plus dot, 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 all the way down to a sub n. Okay, so let's see. First term I think we can clean up pretty nicely. This is epsilon over 2 alpha. We can make this a little bit larger, potentially, by putting the absolute values on the inside. Let's say some absolute value a sub k, and let's just go all the way to infinity. Because we're adding positive terms, we can make that certainly bigger. Okay, so that's gotten bigger. Then let's look at the second piece. We have the supremum over n of beta sub n. Well, that we were calling gamma. And then let's look at this here. We have this times, well, let's see. This is not quite our partial sums because it doesn't go up really, it doesn't start at 0, but it does go up to n. So let's see, if I start with a sub n, well, I have all those terms in the partial sums, but then I'm missing a few at the bottom. So what I'm missing is, if I subtract off, it's a partial sum. I'm missing the first n minus capital N minus 1 terms. So I have n minus capital N minus 1 terms. Well, this, again, we'll put in our absolute values. Here, this is a sub n minus a sub m. Again, because we have this Cauchy sequence, n is certainly larger than our n1 or n2 that we needed, and m is n minus capital N minus 1. And the way we've defined our capital N, that makes sure that n minus capital N minus 1 is still large enough. We can bound this by, this is going to be less than epsilon over 2 gamma. This infinite series right here, that is defined to be our alpha. So let's see what we've got. This is less than or equal to epsilon over 2 alpha times alpha plus gamma times epsilon over 2 gamma. Now you can see why we picked these values, epsilon over 2 alpha and epsilon over 2 gamma, because the alphas cancel out, the gammas cancel out, we get exactly epsilon. So what we've done here is we've shown that this term we wanted to go to 0, this sum a sub k times beta sub n minus k, k equals 0 to n, this is less than epsilon for all epsilon greater than 0. That means it has to be 0. So our theorem is proved. We've gotten exactly what we needed. We've shown that our series, let's see, where did it go? Our series, our sequence of partial sums had a term b times a sub n, which converged to b times a, plus a term that went to 0. So we've got exactly what we wanted. Now this, of course, is not quite the end of the story. There is one other way to look at this. There's a nice theorem that is due to Abel. This is actually very hard to prove, especially with the tools we have now. We won't even attempt to do it. But it says, if I assume that I have two series that are convergent, so some a sub n is a and some b sub n is b, and then the product series converges to c, so we're assuming that the product series converges, then we get that the product series convergence c has to be equal to a times b. Okay, so this requires no absolute convergence on either the series of A or the series of B, but what it does is it does assume that this series converges. Okay, that's different than the last theorem. The proof of this is pretty hard and a bit beyond the scope of what we're going to do in this video.